take a look at a specific function and a specific point. So I've got this function of two variables. It's my usual paraboloid. Okay? And I'm going to look at the point 1, 2. I want to prove from the definition that this function is differentiable at this point. So I've kept up on the board our formula for our candidate for the tangent plane. We're going to construct that, and then we're going to establish that it's a good linear approximation. So if I wanted to create my candidate for the tangent plane, okay, I'm going to need to know f of p naught. Well, that's just 1 squared plus 2 squared. That's 5. I'm going to need to calculate the gradient of f at p naught. Now that's going to be a two-step process. First of all, I have to calculate the gradient function. Then I have to evaluate it at p naught. Much as when you're finding a tangent line of a function of just one variable, you find the derivative function, and then you plug in the specific x value corresponding to your point of tangency. So the gradient of f is just the vector whose components are my two partials with respect to x and then with respect to y. And that's just going to be 2x, comma 2y. So the gradient of f at 1, 2, because the gradient is itself a function of two variables, it's just a vector-valued function of two variables, that's going to be 2, 4. Okay, so now I can say L of xy is f of p naught, we just said was 5, plus the gradient at p naught, we said was 2, comma 4, and we're dotting that with x minus x naught will become x minus 1, and y minus y naught will become y minus 2. I'm going to just work that out a little bit. That's 5 plus 2 times x minus 1 plus 4 times y minus 2. Let's see, that's 5 plus 2x minus 2 plus 4y minus 8. And so let's see, that's 2x plus 4y, and then 5 minus 2 is going to be 3, minus 8 is going to be a negative 5. Okay. Now that's definitely an equation for a plane. If z, which is what L of xy is just a fancy name for, is 2x plus 4y minus 5. Notice, if I had forgotten to evaluate the gradient at my point, if I had had here, instead of 2, 4, I'd had 2x, 2y, then here I'd be multiplying 2x times x minus 1. I'd be getting some x squareds. If you forget to evaluate the gradient at a point, you're generally not going to get a linear function. So that really is very important. Okay, so now I can create the error function. So remember, that's going to be measuring the signed vertical gap between points that are on the graph of this paraboloid and points that are on the graph of this plane. And we define that as f of xy minus L of xy. It is important that we know the order in which we're subtracting them, simply because it is a signed value. Okay. All right, so let's see, that's going to be x squared plus y squared minus this whole thing. So I'm going to just distribute my negative. That's going to become minus 2x minus 4y plus 5. Okay, and now what I want to do is I want to evaluate the limit as xy approaches 1, 2, as an arbitrary point approaches p naught, of this fraction, e of xy, and then on bottom the distance between p and p naught. Now I've just come up with a formula for what I have on the top. So we're looking at the limit. Actually, let me move down here a little bit. We're looking at the limit as xy goes to 1, 2 of this fraction, x squared plus y squared minus 2x minus 4y plus 5. The distance between a point xy and the point 1, 2 is just the square root of x minus 1 squared plus y minus 2 squared. Okay, so I am hoping that that limit is 0. Now, if I've set this up correctly, it should be an indeterminate form. The bottom should be going to 0, and the top should be going to 0. Quick check, yes, they both are. If you don't get an indeterminate form, you didn't set it up right, okay? Because if the points are moving together, the distance between the points is going to 0, and you've set it up so that this plane agrees with the graph of f at the point P naught. So f minus L at P naught will be 0, okay? So, oh dear, we've got an indeterminate form. Well, these two are in a slightly different form. So I don't see any useful substitutions that I can do at this particular point. And we're not approaching the origin, so I can't switch to polar coordinates. But I'm really, really hoping that this limit exists and is 0. It's going to help if I just do a little bit of algebra. I'm going to just multiply out the quantity under the radical here. So this is the limit as xy approaches 1, 2 of x squared plus y squared minus 2x minus 4y plus 5. Here, if I multiply this out, that's going to be x squared minus 2x plus 1. And if I FOIL this out, that's going to be y squared, oh, sorry, this is still under the radical. This is going to be y squared minus 4y plus 4. Oh my goodness, this is lovely, because 1 plus 4 is 5. So now I have on top x squared plus y squared minus 2x minus 4y plus 5, and on bottom I have the square root of exactly that same expression. Now, I can work with this a couple of ways. I could do a U-substitution. I could let U just be this expression. In fact, let's do that. I could say U is x squared plus y squared minus 2x minus 4y plus 5. And so this would become the limit as U approaches 0. Because as I plug in 1, 2, this expression goes to 0. Because we just said the top and bottom are both going to 0. This becomes of U over root U. That simplifies to the limit as U goes to 0 of just root U, right? Because that's U to the first, that's U to the 1/2. That gives me U to the 1/2. Now, you might have noticed that because the top is just the bottom squared, you're going to simply get the square root of this quantity. So you don't necessarily need to do the U substitution in order to see that what you're going to get is just the square root of that quantity. And if you saw that without doing the U substitution, that's totally fine. This is 0. Our function is differentiable at 1, 2. Now that wasn't too bad. But I can imagine that I don't want to use this definition of differentiability very often at all. Because in this particular case, I got this nice connection between the top and the bottom. But the bottom is always going to be a distance between 2 points. So the bottom is always going to be the square root of some polynomial expression in x's and y's. If my function involved any exponentials, or any trig functions, or anything other than some pretty nice powers, I can imagine it's going to be very, very hard to simplify this limit. So the definition is great because it explains what is meant by differentiability. It illustrates that what we want is to have a good linear approximation of our function. But the definition, wonderful as it is not particularly user-friendly except for very specific subsets of functions. Fortunately, there's another criterion. Okay. So, a real valued function of 2 or more variables is differentiable at a point P naught in its domain if all partials exist at and near P naught. So the partials have to exist in an open region containing P naught. And all partials are continuous at P naught. Okay. So if I look at my partial derivatives, if I just calculate my gradient, which will have all the partials in it as its component functions, if those are continuous at a point, and those partials are defined near that point, I'm going to have a differentiable function. This is user-friendly. This is easy to test. One word of caution about this: this is not the definition of differentiability. This is a criterion that guarantees that a function is differentiable. That is different from the definition. I'm actually not 100% sure. I know that anything that meets this criterion is differentiable. It may very well be that there are functions that are differentiable that don't satisfy this definition. I'm honestly not sure. I don't know if this is equivalent to the definition or just a criterion that many differentiable functions satisfy, and that if it's satisfied, we know it's differentiable. So if I ask you on an exam or quiz, what's the definition of differentiability? This is not it. The definition of differentiability is that limit of the error function divided by the distance between my input points is equal to 0. Okay, but this is the user-friendly criterion that we will generally use to see whether we're working with a differentiable function or not.